of AE 240. I have added a couple of you to this team, although they are section 2, because apparently they registered in the past hour, so they should, if they can, if they don't have any conflict, they can attend with us today, and then they will attend with section 2 starting Wednesday, inshallah. Let me start to see, you give me an update. Well, did any of you get the textbook?
Yes, Doctor, I did.
Okay, great. Okay.
Me as well, Doctor.
Hopefully the remaining, the rest of you will get the textbooks. Hopefully, I think by mail. I was told it will. Great. So I have so many textbooks in here. Very good. So please start reading, because we are gonna, although we're gonna go quickly, slow a little bit, the first and second weeks, then things will heat up. So keep following us. Last time we finished chapter 1, introduction, historical perspective from a design point of view. Today and Wednesday, inshallah, we're gonna cover aerodynamics, chapter 2, basically collecting the aerodynamic information from AE 220 that we will need in this course. Then we're going to have next week the propulsion material that we'll need, and then we're going to go into control and design. Do you have any questions for me from last time, or from material posted on Blackboard, or anything? Typically, the first 5 minutes is for any question regarding the course. Anyone? Okay. So, yes.
For the slides, is it enough if I read it instead of the book?
No. Slides is for 50 minutes summary of the material that we have. So you will have to read the textbook. That's for sure. In the slides, we will take 1 or 2 examples on every topic. The textbook has more examples and more problems to practice. So no, the answer is no. Okay. Although it might work for chapter 1, because chapter 1 is a historical perspective, but I think it would be interesting to know the information. But afterwards, no, it will not be enough for the slides. Okay, that's why it's called textbook. It's not a reference book. Textbooks are for reading. Okay, other questions? Okay, so although I had got the attendance of the class now, but realize that as we go, I'll just keep asking randomly. So when I name a question, please either answer if you know the answer, or say I don't know, I don't remember, but please respond. Okay. So I want to make sure everyone are with us here. So I'm gonna stop my video and let's start the what we want to have today. So what we're gonna do is that we're gonna study the aerodynamics of the airplane. And I don't want you just to get lost in here. What we'll do is we're gonna pick and choose from chapters 4 and 5 in AE 220, the aerodynamics and the airfoil. So we're gonna look at the sources of the aerodynamic forces, the lift, drag, and the moment definitions, the moment coefficients, definition of the aerodynamic center, different airfoil characteristics, lift, drag curves, drag polar. So we're going to cover this roughly in 2 sessions. Okay. But before I do so, let me see how many of you have taken AE 220. Can you please raise a hand if you have taken AE 220? Everyone. Great. Everyone. Very good. Okay. Although it's not a prerequisite, it's highly recommended to take AE 220 before this course. So now we can go a little bit faster. When we talk aerodynamics, we basically talk about the motion of air around objects. So these objects could be an airplane, a car, a kite, whatever, anything that has to do with the study of motion of air in here. Then aerodynamics have several applications. It doesn't have to be around the body, flow around the body. It could be flow within the body, inside the body. So we have what we call the external flow applications, flow around wings, aircraft, helicopters, turbines, cars, and so on. And we have internal flow applications where we have flow inside tubes, pipes, ducts, applications of heaters, air conditioners, and so on. Sometimes even flow within heart if we're talking about fluid, flow within the heart and so on. So all these are internal flow applications. Whether they are external or internal, air moving around or inside the body will generate a set of forces because of two main sources. And I'm sure you remember the origin of the aerodynamic forces are either the pressure distribution or the shear distribution around the body itself. The pressure which is normal or the shear which is due to friction around the body itself. Pressure and shear will generate a force. The force will have components. And if I look at the force generated on the airfoil or the wing, we typically call the component normal to the chord line. And now I'm using the term chord line, the line connecting the trailing edge and the leading edge. The force normal to it as the normal force, the force in its direction as the axial force. But I could also resolve the resultant into two other components. One in the direction normal to the air coming, the free stream air, and we call this the lift. And the perpendicular component, or the other one, perpendicular to lift, is the drag component. So I have two axis system, normal axial or lift drag. These are two different set systems. The angle between these two systems is what we call the angle of attack. So the angle of attack is the angle between the free stream and the chord line, or it's the angle between the lift and the normal force, or it's the angle between the drag and the axial force. All of these are the same angle of attack. Okay. Forces are not the only thing generated on the wing by the pressure and friction. Pressure and friction also generate moments on the wing. So if this moment is around the lateral axis, we call this the pitching moment. That's the moment that tends to move the aircraft up or down. Then we have the moment that rotates the aircraft to the right or left, the yawing moment, and of course the other one that tends to roll the aircraft around the longitudinal axis, which is called the rolling moment. So we have pitch, yaw, and roll. Speed of sound is one important parameter that you studied in AE 220 or maybe in physics as well, that we will be using. And I'm sure that you know that speed of sounds depend mainly, speed of sound in air depends mainly on one characteristic, and that is what affects speed of sound?
Temperature.
Temperature. Temperature is the single most important factor on the speed of sound. At 20 degrees, the speed of sound is about 1 kilometer every 3 seconds. That means 340 meters per second. As you go higher, the temperature decreases, the speed of sound decreases. Okay. Now, in your textbook, you don't have to calculate speed of sound. That was back then in AE 220, where you had to study it, or in physics, speed equal gamma RT, root square gamma RT and stuff. No, we will be using the information that you had for design. So I don't need to calculate it everything. You will find an appendix towards the end of the textbook. So I hope you have the textbook beside you. That appendix has atmospheric data, or the standard atmosphere data, where you will have listing of all the important parameters as a function of altitude. Okay, so if you turn your textbook to Appendix B, in there, you will find the altitude, the temperature, the pressure, the density, okay, all as functions of altitude. Now you will find the altitude in both units, the British and SI units, but you will find the temperature, pressure, and density mainly in SI units. Although we will be using both units as we go throughout the course. So feel free to use the appendix in your solutions. In a problem when you need the speed of sound, don't calculate it root square gamma RT, just get it from the tables. The speed of sound leads to the definition of the Mach number, which is the speed of the objects relative to the speed of sound. Of course, in subsonic regime, this is less than 1. Transonic regime, the flight of most transport aircraft, Mach number is close to 1. Supersonic higher than 1 and hypersonic above 1. The transonic regime goes from 0.8 to 1.2 roughly, slightly below and slightly above Mach 1. Then the other number that we need to define is the Reynolds number. So let me hear from Hatim. If you remember, Hatim, what do we mean by Reynolds number?
I don't remember.
Oh, fair enough. That's why we are having this week, just to remember the aerodynamic stuff. If you still have your AE220, it would be wise to go quickly over the material that you prepared for the final exam, which will summarize everything. Okay. Okay. Any volunteers? Reynolds number. I'm not asking what's the definition of Reynolds number. Don't tell me the equation. Tell me the meaning of Reynolds number. What do you mean by it? What does it represent? Any volunteers? Raise a hand. Reynolds number.
I think Mach number is velocity divided by sound of velocity.
Mach number velocity divided by the speed of sound. Khalid, this is the Mach number. Actually, this you are defining the Mach number. It is the speed of the object divided by the speed of sound. That's the Mach number. Okay. Now I'm asking about Reynolds numbers. Let me remind you of the number. If you remember, it was rho VL over mu, density multiplied by speed by length divided by viscosity. So what does that mean, Abdullah Sarhan?
I think it helps us predict fluid motion or something like that.
So Reynolds number helps us determine whether the flow is laminar or turbulent, if that's what we mean by fluid motion. But I think Abdulaziz has a different answer. This is how it helps us. But what does it represent? When I say Reynolds number of this flow is more than the Reynolds number of this flow, what does that mean? You raise the hand, Abdulaziz.
Yes, I just want to say that it tells us about the flow of the fluids.
Yeah, it tells about the flow, but what exactly does it tell us, Sultan?
I think it has something related to viscosity. If we are comparing two flows and one is more than one, then we can say that this flow is more viscous.
Okay, so you all had ingredients of the answer. So let's put everything together and see what it means. Okay, Reynolds number, which is rho V L over mu, and excuse, this is not an alpha, this is infinity. Rho infinity V infinity L over mu infinity. So that's the density of the free stream, velocity of the free stream, some length of the body that's moving in the air, and divided by viscosity. Yes, it tells us something about the flow. Yes, it tells us something about the viscosity. Obviously, the higher the Reynolds number, the lower is the viscosity if everything else is the same. But physically, what it means when I say a high Reynolds number or rho number, you see, if you look at the stuff here in the top, it includes the density of the air, it includes the speed of the air. So it includes everything that had to do with the inertia of the air. Air is moving forward, the things that the kinetic energy, the kinetic force of the air. So if air is trying to move past the object, so he's pushing forward. So that's what we have in the numerator, everything that wants air to move faster around the object. Whereas down there, we have the viscous forces, everything that slows the air down. So it's a ratio between the inertia forces as well as the viscous forces on the air, of air around that body. So the higher the Reynolds number, that means air wants to rush and go faster around the object. If you have a low Reynolds number, that means it cannot go that way. It's slowing down, whether it's because the speed is slow or because the viscosity is high. Whether V is small or viscosity is high, this will reduce Reynolds number. Okay, so keep that in mind. So high flow, high speed applications with high in air and it's being hot, for example, that means you are going to have higher Reynolds number because viscosity is going to be low and the speed is going to be high. But if you have low speed application in cold air, that's going to be low Reynolds number. So just like an aircraft taking off in a European country in the winter. So the takeoff speed is small, so V is small, and the air is heavy and the density, the viscosity is high, so that means Reynolds number is going to be low. But if the aircraft is moving fast in a hot day, that means Reynolds number is going to be very high because the speed is high and the density and the viscosity is low. Actually, Reynolds number is one important reason why if you have gone anywhere, landed in Tabuk, I don't know if it happened to you, but it happened to me twice, that during this hot summer days, aircraft will be delayed, and actually some flights will be canceled, but some mainly will be delayed because it's too hot for the aircraft to take off. What happens is that the runway is not long enough for the aircraft to take off if the air temperature is beyond a certain limit. So you have to wait for a while until the air cools down, viscosity increases, the Reynolds number go down, and the aircraft can take off. So Reynolds number is very important in determining the lifting and drag forces on an aircraft. Okay, now defining the forces and moments that we had, you moved on and you defined. You have a problem with the sound?
Yes.
Yes,
Doctor.
Yes.
There is a problem with the sound?
yes, Doctor. Not stable.
Let me see what I can do. Let me try something on to our network. Now, is that better? Hello?
No, Doctor.
No,
Your voice,
good?
yeah. No, not
Okay.
good.
Okay.
Still not good, Doctor.
I think the
Not
problem
good.
is with the connection.
Yeah, I keep getting bad network quality, but I am on KFBM network. Let me try the Wi-Fi. It will be better. كده يا شباب افضل شويه.
لا أعتقد صار أسوأ.
اسف. Just give me a second here. Now it's fine. Now it should be. That's the land should be okay now. شباب
نفس الشيء.
نفس الشيء ما فيش تغيير.
لا.
How come I hear you very well?
Doctor, we hear each other very well, but when you speak, the sound.
I think it depends on your internet connection. Maybe
No, it's this one is. I tried the Wi-Fi, KFBM Wi-Fi. Now I'm in KFBM network. It should be better than the Wi-Fi.
Now.
Yeah, now it's good.
Without.
Now it's okay.
Yeah, Doctor.
Yeah,
I can hear you very clearly.
Okay. Sorry for that. So let's get back to business here. So you define the coefficients, the lift coefficient, drag coefficient, normal force coefficient, axial force coefficient, moment coefficient, simply by dividing the appropriate force or moment by the dynamic pressure and the area. But we have to agree on what do we mean by the area when we say the reference area. When you divide by an area in order to get coefficient, it is the plan form wing area. It's the two-dimensional area. It's the projected area of the wing, not the upper surface area or the lower surface area of the wing. When you are talking about a moving sphere, for example, in air, the area that we have is the cross-sectional area, what we call the projected area. The characteristic length, you see this L here, when you're talking about wing, what is a characteristic length in the case of a wing? What do you call it?
Airfoil?
Yeah, the airfoil is the cross-section of the wing. What is the length of the airfoil that we use? What did we call? The chord line, right? The chord length is the characteristic length of the airfoil. When you divide by L here in order to get coefficient of moment, this L here is the length or the chord of the airfoil, okay? But if it's a sphere, for example, then the length we are talking about is the diameter, okay? Remember this characteristic length that we have in here, or even in Reynolds number definition in here, that characteristic length is the length in the direction of the flow. Now that sometimes make students get confused when they are calculating lift or drag for a fuselage. For a fuselage, what's the characteristic length? What do you mean by characteristic length? If you are calculating Cm, for example, of a fuselage, you divide the moment by the dynamic pressure by S, and we agreed S is the cross-sectional area, by L. L here is not the diameter of the fuselage, okay? There is like people would like to think, oh, the dimension of a fuselage is the diameter. No, it's not the diameter. It is the length of the fuselage. Why? Because it is the dimension in the direction of the flow. The length that we have here is the dimension in the direction of the flow. Okay. So for a fuselage, it is the length for Reynolds number. Let's move on to our first problem. And the objective of the examples that we have here is not to test your aerodynamic information, because we assume you already have them now, but to start to get a feeling of the numbers. For example, in this problem we have here, we will calculate the lift coefficient of a Boeing 777 that has a certain wing platform area, 4,605 square feet. Assuming that the takeoff weight of this aircraft is 506,000 pounds and the takeoff velocity of 160 miles per hour, calculate the lift coefficient at takeoff for the standard sea level conditions. So it's required to calculate CL. And then it's required to repeat the whole thing, compare again, calculate again CL, but for when the aircraft is cruising at Mach number 0.83 at 30,000 feet, assuming the same way. Now that should be a very simple problem for an A220. I mean, trivial, I would say, why he's bringing this. There is a point that I need to raise after we solve the problem. So any suggestions? How are we going to calculate CL for part A?
We have the weight, we can consider it the lift force.
Yes.
And we can find the dynamic pressure because we have the speed and
you have, yes.
And at sea level we have the density. So
right.
we can put the number in the equation.
Right. So we'll get the number. So we have everything there, and that's correct. So as your colleague mentioned, here we have the speed, but maybe I need to convert it to meter per second. So I need some conversion table. I have the density at sea level, so I know the dynamic pressure. I have the lift is equal to the weight. I have the wing area, the only unknown is CL, turns out to be 1.68. At a certain altitude, 30,000 feet, I will repeat the whole thing, but I don't have the speed, but it's okay. I have the Mach number, okay, 0.83. Then I will multiply it by the speed of sound at this altitude, A at 30,000 feet. Then I will get V and I will do the same thing. I will get a CL of 0.362. So what's the point here? We already know this. Yeah, the point here is that I want you to develop a sense of the numbers that we have. Because in design, we will go the other way around. In this problem, I gave you the wing area of the aircraft and we were calculating what CL. But when we are talking design, it has to be the other way around. Remember, when you design, that means you don't have that thing physical. I don't know what's the wing area. I don't know S. So in order to determine the wing area and make a rough estimate of it at the beginning of the design, as we will do in week 4, I have no more equation than this one, but I have to use it differently. At that time, I will probably know the weight of the aircraft or an estimate of the weight of the aircraft, because I know I need to design an aircraft that will carry 20 people, for example, certain amount of luggage, and it's made of aluminum or composite material, and it will carry certain amount of fuel. So probably I will know the weight, just like in this problem. I probably be able to know the dynamic pressure because it will take off from sea level conditions. So I know the density. It will take off at a certain speed. I will know this maybe from the regulations. It tells me that takeoff speed has to be at most a certain speed. But what I will not know is the area of the wing as well as the CL. So I will have two unknowns in this equation. So in week 4, when we design that wing, I will need to assume a value for CL in order to get the wing area. So I don't want you to go there in week 4 and assume a takeoff value of CL of 0.1, no, of 0.2, no, of 100, no. Reasonable values for CL for transport aircraft are somewhere during takeoff between 1.5 and maybe 2.5, 3 at most. So that's the range. So I need you to start to develop a sense of these numbers. They're just like in the top of your mind. It's just like if you have, when you talk about speeds of cars, you are experts in this. You know that 40 kilometers per hour is too slow for a car. You know that 300 kilometers per hour is very high for ordinary car. So you know that the maximum speed of an ordinary car, we are talking between 150, 60, 240. You know that range, right? I want you to start to develop that capability for aerodynamic numbers. Reasonable value for CL during takeoff, somewhere between 1.5 and 2.5, maybe 3. Whereas CL during cruise, the situation is different. Why would I need CL during cruise? Because I need maybe to design the wing of a transport aircraft, not based on takeoff conditions, but on cruise conditions, because this is the phase of the flight where I will be burning most of the fuel. So I really want to determine the wing area based on cruise conditions. So in this case, I have the weight, I have the dynamic pressure, but I don't have the area and I don't have CL. So in week 4, we will assume a reasonable value of CL. I don't want you to go and assume it 1 or 2. That's very high, way too high. Reasonable value for CL during cruise for an aircraft, we are talking between 0.25, 0.3 up to maybe 0.6. That's as high as it gets for cruise for a transport aircraft. Okay, so let's start developing this sense as we go in the first couple of weeks. Okay, it's not the answering of the problem, it's the result that I need you to remember that here. Any questions so far? Any? Now you see why this CL is higher than this CL, because the speed here is faster than the speed here, right? So you don't need as high as CL as in this one. How would the same wing, this is the same wing of the same aircraft, how would it generate 0.362 during cruise and generate 1.68 during landing? How do you do that physically? What changes in the wing in order to change that CL?
The angle of attack?
Angle of attack is the main parameter. Of course, the pilot would pull the stick backward or forward to increase or decrease the angle of attack. This is one parameter, of course, the angle of attack. The other parameter would be the deployment of high-lift devices. Maybe even with increased angle of attack, I cannot get to the 1.68. Maybe I can get to 0.9. That's the maximum I can get with a clean airfoil. Maybe 0.9. In order to get beyond that, I will need high-lift devices. I need flaps, I need slats in order to increase that CL to 1.68. So yes, as you mentioned, the angle of attack here is an important parameter. So the variation of CL with the angle of attack is very important. You all know that it's almost linear for a range of angle of attack, roughly to 8 degrees, 10, 12, 14. Then it starts to be slightly nonlinear up to the maximum angle of attack, say 20, for example, and then we are going to have stall, where the air will separate. Okay.
Doctor?
So stall can appear. Yes.
I have a question.
Yes.
You gave us the CL for takeoff and CL for cruise. What about
Yes.
CL for landing? Is
What
it the
do you
same
think?
as takeoff?
Let's see. Your colleague wants to add here part C during landing. Let's see what's the difference between landing and takeoff, between part A and part C. Typically, aircraft would take off at slightly higher speed than landing speed. Okay, Ideally, landing speed would be almost the stall speed, and takeoff would be like 1.1 the stall speed. So takeoff is slightly faster than landing. Okay, slightly, not much. So if the speed is higher, what do you think the CL is going to be? Higher than the 1.68 or lower than the 1.68?
The speed of the takeoff is higher.
Speed of takeoff.
The CL of landing will be lower, I think.
What? Let me put it this way. V landing is lower than V takeoff. So CL landing has to be higher than CL takeoff to generate the same lift. Right?
Yes.
It has to be higher to generate the same lift. But there is a catch here. The catch is the weight during the landing is not as the same as the weight during the takeoff, right?
Right.
So if the weight of the landing is way lower than the weight of the takeoff, then maybe CL would be the same as the 1.68 or sometimes even lower. It all depends on the weight and the speed, okay? But sometimes for safety, we assume that the weight of takeoff is the same as the weight of landing to allow the aircraft to land right after takeoff if there is an emergency. Assume a pilot has taken off and there is an emergency and he has to land, okay? So in this case, the landing weight is almost the same as the takeoff weight. The speed is lower, so the CL has to be higher. Okay. So CL landing more than CL takeoff in general. Okay, sure. Stall occurs at either very high positive angle of attack or very high negative angle of attack. In both cases, we have stall, which reduce lift, drag, and moment and increase moment considerably. Okay. Also, the angle of attack affects not only lift, but it affects also drag. Of course, there is an angle of attack at which drag is minimum, where we have CD minimum drag, or the one that we call the CD naught. But angle of attack is not the only parameter that affects the drag. Reynolds number also affects the drag. The higher Reynolds number, the lower the drag is going to be. So these curves have higher Reynolds number as you go from the inner one to the middle to the outer. You increase Reynolds number, the drag will go down in general. Okay. Then we have some definitions of two important points that I need to check with you before the next part. The two important points are basically the aerodynamic center and the center of pressure. So I need a volunteer to distinguish between these two. Either tell us what is any one of them, or distinguish between the 2 points. I need you to define what's the aerodynamic center and the center of pressure. Any volunteers, raise a hand.
Can you repeat, Doctor, please? What you said?
What is the aerodynamic center? Hello?
Yes, Doctor, I'm just thinking about it.
Okay. Abdul Aziz Thiban.
I'm not sure, but I think the aerodynamic center is the point where the aerodynamic forces are equilibrium.
Forces on aerodynamic, the point at which aerodynamic forces are in equilibrium. Well, I have a couple of problems with this definition. One, aerodynamic forces and inertia forces and the weight are always in equilibrium if we're talking straight and level flight, right? So doesn't seem to be very accurate. Okay, who else? Sultan?
Yes, for the center of pressure, I think it's where the lift happens, or the point where the lift acts.
Okay, the lift, where the lift acts.
Yes.
Okay, actually, I would combine your definition and that of Abdulaziz, because the correct definition is a mix of both. The center of pressure is the point at which the resultant aerodynamic force acts, whether it's a lift or a drag, all of them, the resultant R acts at the center of pressure. You have a pressure distribution around the wing. It has a resultant. It acts at the center of pressure. So mixing your definitions together works fine. I hope Yusuf will tell us about the aerodynamic center. That's the second one that we have.
Yes, doctor. The aerodynamic center is the point where the moment coefficient doesn't change when the CL changes.
Perfect. Perfect. Okay, so the aerodynamic center in here is a point at which the moment, about which the moment does not change with the angle of attack. Not changes in general, because it will change if the aircraft slows down. It will change if the density changes, but it will not change if the airfoil rotates. If the angle of attack changes, the moment coefficient about the aerodynamic center does not change. That's the definition of the aerodynamic center. So, and why it's important? Because I can use it to calculate the moment about. By calculating the moment about it, I can look at the aircraft flying at different angle of attack without worrying that the moment will change. It will not affect my equations. Typically, the aerodynamic center occurs at the quarter of the chord. So that's where the aerodynamic center lies, and the moment does not change with that angle. Whereas the center of pressure is the point, as Sultan and Abdulaziz mentioned together, where the resultant of the pressure distribution acts. Okay, it's not only the lift, it's the resultant force, which can be resolved to lift as well as drag. Okay, what's the moment about the center of pressure? What's the value of the moment about the center of pressure? Anyone?
I think 0, Doctor.
0, because if the resultant is passing through the center of pressure, then there is no moment around the center of pressure. Okay, the center of pressure has a 0 moment. Okay. Our next step would be the language that we will use when we talk about the airfoil. So I will just remind you of the different nomenclature that you had in airfoil. You defined, of course, the leading edge of the airfoil, the trailing edge. The line between them is the chord line. The dotted line here in the midway between the upper and lower surface is what we call the mean camber line. The maximum value of that mean camber line above the chord line is called the camber. Okay, and I'm sure you studied some families of airfoils that differ in one or more of these characteristics. Am I correct? Did you study airfoil families with Dr. Gardner?
I don't think we studied them in a lecture. Not yet.
No, what do you mean not yet? You are still taking 220 or you have finished 220?
Yeah, I finished 220. I don't remember taking
airfoil families. So when I say airfoil 20, yes, go ahead.
But I didn't remember because there is a lot of we take the lift and the drag coefficient in each airfoil.
Okay, so when I say a 4-digit family of airfoil, you know what I'm talking about? When I say airfoil 2014, does that ring a bell?
No, we didn't take.
Okay, fair, that's good. So let's go slower on this. Now, based on the number of thickness or camber or the location of the camber, we can change the shape of the airfoil. And of course, we will change the lift and drag. So I can make it even more curved or maybe a symmetric airfoil. So we have families with difference in these numbers. And I will leave you with just the names of the families, but I will go in details on them next time. We have what we call the 4-digit family, because the name consists of 4 digits. Okay, it's just like when you talk about the Mazda family of cars. You have the C5, C3, C5, C7, C9. Okay, so that's the family. So we have a 4-digit series family of airfoils by NACA. It's 4-digit because it has 4 digits. Then we have the 5-digit series because it has 5 digits. Then we have the 60 series. It's not, oh, that's a typo, not 6-digit. It's 60 because it starts with a 60 something, 62, 63, 64. And then we have what we call the symmetric or biconvex families. So we have some families, and each family, just by looking at it, I can determine a lot of information about that airfoil. Okay. For example, some cars have the, when you say CX 2.7, for example, that tells you that the engine size is 2.7 liters, 1,700 cubic centimeters. The same goes for airfoils. When I see a NACA airfoil, 4 digits, 2412, I look at the last 2 digits and I know that this is the thickness ratio of the airfoil. So these 12s tell me right away this airfoil has a thickness that's 12% of the cord. So the thickness, 12% of the cord. Maximum thickness is 12%. So if I have a member of the same family that has the last 2 digit 15, I know it is a thicker airfoil. 18, that means even thicker airfoil, and so on. When I look at the first digits in the family, it tells me the camber of the airfoil. So this 2 means the camber is 2%. What does 2% means? Means that this small distance here between the center line and the camber line is 2% of the whole cord. Okay, 2%. The 2. If I have another member of the family, instead of the 2, I have 5, mean this distance is 5. That means the airfoil will be curved more. It's a curved airfoil. Okay, so the first number here is the camber. The last 2 numbers represent the thickness ratio. So the thickness ratio is 12%. The camber is just 2%. And the second number tells me the position where this camber is. Where is the maximum camber? So in the figure that we have, this is the maximum thick camber here. It occurs maybe at 20% of the cord. If that's the case, I would put 2. If that distance here is 40% of the cord, then I will put 4. So I can simply draw this airfoil simply by looking at its numbering. Airfoil 2412. See if you can see this on the board. Can you see the board?
Yeah, we can.
Oh.
Yes, doctor.
So I can draw the airfoil 2412.
Doctor, the green not clear.
The what?
The green color not clear.
It's not. Okay. I have an airfoil 2412. Now it's clear? Not really?
Clear and blue, we can see.
Oh, you cannot see the blue. Okay. Well, I guess.
Doctor, I can't see the board.
Oh, you can see the board itself.
Yes,
Okay.
me too.
Yes. I think I will have to draw it next time then, because we are almost time. So I'll make sure to arrange something to show you how to draw an airfoil if you know the numbering system of that airfoil. Actually, we were supposed to stop right before the airfoils families here. So we're gonna continue this next time, and we're gonna draw that. Meanwhile, I need you to do the reading for chapter 1 and the part that we covered in chapter 2. So we're gonna continue on the aerodynamic summary on Wednesday inshallah. Let's see if we have a better connection. Okay شباب شكرا.
دكتور وائل طلع طيب قال في كويز شيء؟
لا ما قال في كويز ولا شيء.
ولا يحضر صح؟
ايه
انا
لا التحضير قال الكتروني، مجرد دخولك لهذا يبان.
إيه.